We have spent the last 3 or 4 weeks, no, three weeks, trying to build up our knowledge of functions that have proved useful in science and engineering and mathematical settings. And basically we started off with the absolute value function, then we had some of the polynomial functions, and we know about horizontal lines, linear graphs and parabolas at least. Should learn about cubics and so forth as we go along as well. So the polynomial functions. We then had the exponential and logarithmic functions, and the last class of functions that we're going to cover are the trigonometric functions sitting there. So that's our last lot of functions before we get on and do some calculus. So that's what I'm going to be concentrating on. Well, first of all, let me tell you why we like the trigonometric function. So here's a picture of one of the trigonometric functions. It's the graph of sine x. But if you look at the graph, it has a completely different nature to the other functions that we have looked at. In that, as x goes along here, if we go along the x-axis, this graph just keeps going up and down, and it keeps repeating itself forever and ever in both directions. So it goes, that graph continues on out that way and down this way. And so if you have a phenomenon that you're interested in, and it's periodic, it repeats itself. For example, if you were trying to model the tides, right? Comes in, goes out, comes in, goes out. It keeps repeating itself. Modelling a pendulum, backwards and forwards, backwards and forwards. This is the type of function that you will want. Okay? So if we've got periodic phenomena, then we will need trigonometric functions. Our things like exponential functions, they're good for modelling things like population growth. We saw logarithms were good for earthquakes. Polynomial functions are good for all sorts of things. But we do need to add this one to our repertoire. So that's what we aim to do. So trigonometric functions are useful for modelling phenomena that vary periodically. Okay. In order to understand the trigonometric functions, however, we need to start off with the trigonometric ratio. So I'm going to assume you know nothing and start from scratch. I hope that's not demeaning. Okay, so here we go. So we're going to start off and look at the trigonometric ratios, and then once we've got a bit of a exposure to that, then we're going to move on and show how that develops into the trigonometric functions. That's our plan. So let's go. We're going to start by looking at trigonometric ratios. I might zoom that one out just a little bit. Go the other way. Oh. Okay, that's as good as it can do. Go there. Okay. So, trigonometric ratios are useful when we're studying triangles. And the basic idea of these things are, when you have a triangle, we know basically there's 6 pieces of information in a triangle. There are 3 angles, which we tend to denote by capital letters. So we've got the vertices are A, B and C, and we tend to call the angles A, B and C as well. So they're capital letters for the angles. So I might just put in here capital letters. This is just a convention. You don't have to do it, but that's what's usually done. We use capital letters for the angles, and for the sides we use lowercase letters. And by convention we put the lowercase a opposite the angle A. So this is side little a, side little b, and side little c is opposite angle capital C. So in this triangle there are 6 pieces of information that we can know about that triangle. The question that we want to ask is, how many of these do we need to know in order for the triangle to actually be set? So if I know just one angle, is that enough to determine the triangle? And the answer is, of course it's not, because I could draw another triangle out here that had longer sides, even if it had that angle. If I have an angle and two sides, is that enough? And so forth. So that's the question. How many of these 6 things do I need to know in order to know them all? 2 is your guess. Okay, good guess. Wrong, but a good guess. Okay. Now, that question, first of all, is a little bit too difficult. So before I can answer that question for triangles in general, I need to go back and work with just right-angled triangles. Okay? Once I know about right-angled triangles, then I can come back to the case where we're just talking about triangles in general. So, let's introduce some terminology to go with right-angled triangles. So, in here, here's a right-angled triangle. A right-angled triangle, obviously, I think is a triangle that has a right angle in it. It can only have one right angle because the angle sum in a triangle is 180 degrees. And there are 3 of these things, so there can only be one that's 90. Okay? So we've got one right angle. The side opposite the right angle is called the hypotenuse. It's the longest side. So the hypotenuse is always opposite the right angle. Opposite the right angle. Whoops. And it's always the longest side. It's the longest. If I have one angle that I'm interested in, let me say it's here at A, then the side that isn't one of the arms of angle A is called the opposite side. So this is opposite with respect to A, with respect to angle A or theta. Likewise, the non-hypotenuse side of that angle will be the adjacent side. So with respect to A, also with respect to A, sitting in there. So that's the notation and terminology that goes with it. Now, sitting in this triangle here, there's a few things that we know already. The first thing that we know is that the angle sum is 180 degrees. The angle sum is 180 degrees. Now, in here, I already know that I've got 90 degrees at C, I've got theta degrees at A, so this angle up here must be 90 minus theta, so that when I add them up, 90 minus theta plus theta gives me 90, 90 plus 90 gives me 180. So given that I know this angle is theta, I know angle B is 90 minus theta. So that implies angle B is 90 minus theta. I know that. The other thing that I know about right-angled triangles is I know Pythagoras' theorem. So I know Pythagoras' theorem. And it says that A squared plus B squared is equal to C squared. That side squared plus that side squared is equal to the hypotenuse squared. And that is true for every right-angled triangle. Okay. We've now got enough terminology that we can now start investigating this problem here. How many things do we have to know in order to answer or to work out the whole triangle? And the whole basis of this is to consider two right-angled triangles that have an angle of theta. So I'm going to say, let's draw another right-angled triangle. So I'll say here, consider another right-angled triangle. That's supposed to be triangle there, with an angle A, I might call it A dash, is equal to theta. So I'm going to draw another one. I'll draw it here, say. So here it is, there it is, like that. So it's got a right angle, it's got an angle there that's theta. And let me call this triangle A dash, B dash, C dash. That's not a dash there, that's theta. So it's not necessarily the same size, but it has 3 angles the same. Triangles that have 3 angles the same are called similar triangles. So let me come over here. So what I've done on the next sheet, just go there, is I've drawn these 2 triangles on top of each other with A and A dash in the same spot. So here it is, oops, there, and A dash is equal to A. So here's my little triangle, here's my big triangle. As we said before, we know that angle has to be 90 minus theta. Now likewise in my little A dash B dash C dash triangle, theta plus 90, so this angle here must also be 90 minus theta. So those 2 triangles are indeed similar. So I'll say triangle ABC is similar to triangle A dash B dash C dash. And by is similar to, I mean have the same angles. So the side lengths aren't necessarily the same, but the angles are. Oops, that's useless. Let's put it there. Have the same angles. And there's one very important fact about similar triangles that you should know. I don't know if you do. Does anyone know the important thing about similar triangles? Nobody's quite game to say. The important thing about similar triangles is that the ratio of corresponding sides are equal. So that implies that the ratio of corresponding sides are equal. That's a well-known property of similar triangles. So for example, in here, in my big triangle, I would call that side A, I would call that side from there to there B, and I would call this side here from there to there, oops, I should call that C, that's opposite C, and that's opposite B. In the little triangle, that will be side A dash, that side there will be B dash, get it wrong again, C dash, and this side here should be B dash. So this says the ratio of corresponding sides. So in other words, I can pick any pair that I like. So I'll just say, for example, I would say that the ratio of A dash to C dash, so the ratio of A dash to C dash, should, in that triangle, the ratio of that side to that side should be the same as the ratio in the big triangle of A to C. They are corresponding sides in each triangle, so their ratios will be the same. And I can pick any 2 pairs. So I could, for example, say, look, the ratio of B dash to C dash should be the same as the ratio of B to C in the bigger triangle. What other pairs can I pick? Why don't I go A dash to B dash should be A to B. And in fact, I could pick 6 different pairings there if I could like. I could then go the ratio of C dash to A dash, C dash to B dash to A dash, sitting in there. Okay? But 2 triangles, ratio of corresponding sides are equal. Now these ratios, because they are equal, are given names. And the name given to each of these is, this one's called the sine of theta, because the value of the ratio will actually depend on the angle sitting here. If I were to draw a different right angle triangle that had a different angle, those wouldn't be similar, and so the ratios won't hold. It's because both of these right angle triangles have an angle of theta there. And so that's called the sine of theta, that ratio. This ratio that I put in here is called the cosine of theta, and the last one is called the tangent of theta. And I must admit that I'm not exactly certain of the origin of those terms. As in, I don't know why they're called sine, cosine and tan. But we denote them like this: sine theta, cos theta and tan theta are the shorthand versions of those. Now, sitting in here, I have written this as sine bracket theta. As you read your maths books and go on the web and so forth and look, quite often you'll see no brackets there, it'll just write sine theta. And that's perfectly acceptable, common practice. I, however, really like to use this with the brackets because come next, well, I don't know, probably next Tuesday, we're going to talk about the trigonometric functions. And so this is to remind me that this is going to be a function. That's function notation, the same as we had log theta and so forth. The log was the name of the function. Sine's going to be the name of the function. So I like to use function notation. Okay? So I'm always going to put the brackets there. As I say, it's not necessarily the thing to do. So, out of this, the conclusion is that in any right-angled triangle with an angle of theta, each of these ratios, now if you have a look at sine here, I said it's the ratio of A to C here. So it was the ratio, and if we go back to our triangle here, it's the ratio of A to C, so it's the ratio of the opposite to the hypotenuse, is sine. Likewise, cosine is the ratio of the adjacent to the hypotenuse, and the tan was the ratio of the opposite to the adjacent. So here I've actually taken the liberty of writing them out. Instead of just using A dashes and C's, I've actually used opposite and hypotenuse sitting in there. So they are the 6 possible pairings that I could get. And so in any right angle triangle, each of these ratios are constant, and that is the basis of all our trigonometry. So we are going to make use of this for the next 3 lectures. Okay, so important is the idea. Now, in here I've just put the shortened version. So CSC actually stands for cosecant in there. This one stands for secant, and this last one stands for cotangent. The words sitting in there. So the cosecant of theta is the ratio of the hypotenuse side to the opposite side. It doesn't really logically matter, but once you've got 3 of them, you can get the other 3 just by taking the reciprocal. You can see that the cosecant is 1 on the sine. Likewise, the secant is 1 on the cos, and the cotangent, I haven't spelled adjacent right there, as you can see, but anyway, is 1 on the tan. So if you know 3, you can work out the others quite easily. And as a result, these 3 here are the ones that we tend to work with all the time. So these ones are called the principal ratios. Principal ratios. And these ones are called the reciprocal ratios. And as I say, we could have done it the other way around. It wouldn't make any difference to the overall scheme of things, but we had to choose one lot. And so we've chosen the sine, the cos and the tan sitting in there. And so as I say, that's what we need to keep in mind for the rest of today, Thursday and next week. Okay, just that one box. Get that, we've got everything, sort of. Now, the beauty of all this is if there's some triangle for which I know what these ratios are, then I can apply those ratios to any other triangle that's similar to it. Okay, so the important thing is, can I find one triangle where I know what's happening? And the answer is, in some cases I can. I can find some triangles where I know what's going on. Yep, I'm going to leave that there. So, for 30 degrees, 45 degrees and 60 degrees, we have very simple triangles that will help us out. So I say, we know the trigonometric ratios from these following two right-angled triangles. And I guess in here, the first one is in fact an equilateral triangle. Equilateral triangle with sides of length 2. Now, an equilateral triangle has all sides equal and all angles equal. So 2, 2 and 2, and the angles are all 60, 60 and 60. Now what I do is I cut that in half. I produce therefore a nice right angle triangle, and the angles 60 and 90, so that one must be 30, we know. This side here, it's split in half, so that side is of length 1, that side's of length 2, and so via Pythagoras' theorem I can work out that this squared plus this squared has to be 2 squared, so that side has to be the square root of 3. So here's a right angle triangle in which I know the angles and in which I know the sides. So this was worked out via Pythagoras' theorem. Via Pythagoras' theorem. In there. So there's one of my special triangles. It's the equilateral triangle one. The other special triangle is the isosceles triangle of side length 1. So this one is an isosceles triangle with side 1. And so an isosceles triangle has two sides the same. And if I put my right angle with here from the arms that are side length 1, then because in an isosceles triangle the base angles are equal, though that angle there has to be half of 90, so the angles have to both be 45. And by Pythagoras' theorem, the hypotenuse has to be the square root of 2. 1 squared plus 1 squared is 2, square root of 2 squared is 2. So here, for a 45-degree isosceles triangle, we know the sides and we know the angles. And as a result, I can produce a nice little table like this. I can say, look, the sine of 30 degrees. Here's my triangle. Here's 30 degrees. For 30 degrees, this becomes the opposite, and this is the hypotenuse. And so the sine of 30 is opposite over hypotenuse, that ratio, so it's a half. So the sine of 30 degrees is a half. Now, if I wanted to do the sine of 60 degrees, then here is my angle here. So now the square root of 3 is the opposite, and 2 is the hypotenuse. So the sine of 60 degrees is the square root of 3 on 2. Sine of 60 degrees is the square root of 3 on 2. So this is opposite, and I guess say for 60 degrees, whereas this one was opposite for 30 degrees. So it's depending on where your angle is as to which side is the opposite side. Likewise for sine 45 degrees, it doesn't matter which one of these I choose. Let me choose this one. The opposite is 1, the hypotenuse is root 2. So the sine of 45 degrees is the ratio of the opposite to the hypotenuse, so it is 1 on the square root of 2. And if I go through all of my ratios as put here, then I can work out all of these values here. And I could also work out cosec 30, the cosecant of 30. Let me just quickly write it down. Look, have a look here. It's hypotenuse on opposite. So if I wanted to, I could go, look here, note cosec theta degrees would be the hypotenuse, which is 2, on the opposite, which is 1. So cosec of 30 would be 2. And of course, that is 1 on the sine of 30 degrees. It's the reciprocal of the sine, if you like, in there. And I could do that for all the other ones. I could work out the sec 30, sec 45 and so forth, and the cot of each of them. You could try, I mean, this table is going to be important, so let me highlight it. That says important to know, or you'll want to refer back to this. You could put that on your cheat sheet, I guess. You could try to memorise it, I guess. Or alternatively, you just remember that I've got an equilateral triangle of side length 2 and an isosceles triangle of length 1. And just draw that triangle. It doesn't take long. It doesn't matter. I mean, the other thing is, as you probably know, your calculator has buttons on it for these sorts of things. Your calculator more likely, however, to give you an approximation, because these are square roots sitting here. It'll give you the right answer there, it'll give you 0.5. But sitting in here where these are irrational numbers, these surds, your calculator will only ever give you an approximation rather than an exact value. So these values here are exact in there. We can get the exact value for other angles other than 30, 45 or 60, but I'm not going to expect you to be able to do that in this course. If you know these ones, that's good enough, I will say. So, we have said in any right-angled triangle, we know these ratios. We know these ratios for a particular triangle, so now we can actually use these to help us with an unknown triangle. So let's do it. It says, find all sides and all angles in this triangle in here. So in here, oh, that should be a right angle in there. I should have changed that. That's a right angle triangle sitting there. So you don't have to, you wouldn't write this down in an exam, but I'm writing it down just because I want to explain what we're doing. Here we have been given one side. In this case, we'll call that C, I guess. I guess it makes sense to call that A and that one B. So we've been given that little c is 4. We've been given the length of the hypotenuse in this triangle, and we've been given one angle, although we know the other angle here, we actually know it's a right angle. So I would say we've been given one side and two angles, I would say, in here. And the angles we've been given is C is 90 degrees and A is 30 degrees. We want to try to calculate B, capital B, little a and little b. So the belief is that if I know 3 things about the triangle, then I know all 6. Okay, that's what we think. So, to start off with, we can find angle B very easy because we know that the angle sum in a triangle is 180 degrees. And I know 30 and 90, that's 120, so that has to be 60 degrees. So that's the first thing. So I'll say since the angle sum is 180 degrees, that implies that angle B is 180 minus 90 plus 30. So minus C plus A. And so in there I get 120 degrees. I get 60 degrees. 180 minus 120. So that angle is 60 degrees. That's good. So now I know all three angles. Can I work out the sides? And what I'm going to do is, look, I know the value of sine 30. I've got it sitting over here in this table. It says sine 30 is a half, always a half. So now I know that the sine of 30 degrees will be the ratio of the opposite to the hypotenuse. So that's A over 4. But the sine of 30 I know from another triangle, from our special triangle, is a half. So therefore I have A over 4 is equal to a half. And so that tells me that A has to be 2. So because I knew about the sine of 30 degrees from my equilateral triangle, I can use it in other triangles. And that's what I've done. I can use it in triangles other than this, so long as the angles are the same. And likewise, now to find B, I've got two choices. I could say that the cosine, note, here, the cosine of 30 degrees will be adjacent over the hypotenuse. So for 30 degrees, that side B is the adjacent. And so that would be B on 4. The cosine of 30 degrees we have as the square root of 3 on 2, according to the box. So I have the square root of 3 on 2 is equal to B on 4. So B must be equal to 2 root 3. And so I found B. Now, in this case here, I didn't mean to put the note there. I said that's what we do. I would say here, note, this is what I wanted to note. I could have found B via Pythagoras' theorem. So I could say by Pythagoras, I could say that B squared plus A squared, and A is 2, has to be equal to C squared. So rather than using cos theta, I could have used Pythagoras' theorem. So this tells me that 16 minus 4, so B squared is equal to 12. So therefore, B is equal to the square root of 12. And I know it's not the negative square root because we're talking about the length of a triangle. So it has to be the positive square root in that case. Now, the square root of 12 is the square root of 4 times 3, and so that becomes 2 root 3. So either method is fine, but the important message is, once we know one side and two angles, we know everything about that right-angled triangle. We know everything about that triangle. And that's trigonometry in a nutshell. Sorry? It's a big nutshell. Yeah, but it's doable. As I say, if you understand this box here, you should be right. This is the fundamental thing to get. Understand what these mean and where they came from. If you can do that, I reckon you can master most of this stuff pretty well. Get out of there, piece of paper. Okay, so sitting here, just before I cover this up, we got the exact values of our trig ratios for 30 degrees, 45 degrees and 60 degrees. As you can imagine, not all triangles are 30, 40, 30, 45 or 60. There are plenty of other angles that will crop up in lots of situations. So we would like to do the same thing as we've done here, only with other angles. And I guess the best thing for me to say at this stage is we know the exact values of the trig ratios for 30, 45 and 60. We can work them out for a few others as well, like 15 and 75, but we're not going to. But there's plenty of angles for which we don't know the exact values, and for those angles we're actually going to use our calculators. How does your calculator know how to do it? Well, you're going to have to wait till you get into Math 1120 before we can show you how your calculator knows how to do it. Okay? But needless to say that somebody somewhere along the line has worked out how your calculator can do it, and it's all been nicely programmed in there for you and you don't have to worry about it for the moment. Okay? Unless you're losing sleep at night over how your calculator, in which case you can come to me and I'll give you a quick lesson. All right. So here we go. So for example, get out your calculator if you happen to have it with you and just see. First of all, make sure your calculator is in degree mode, because as we'll talk about very shortly, your calculator can be in either degree mode or radian mode. So make sure that you know how to get your calculator into degree mode. That should be the default. It should come up automatically in degree mode, but it may not. So put it into degree mode and see if you can get it to do these things. The sine of 48, the cosine of 32.5 degrees, and the tan of 2.71 degrees. So I'll just say here, make sure your calculator is in degree mode. Most calculators have degrees, radians or gradians. We're not going to talk about gradians at all, but we're certainly going to talk about radians down the track. So you will need to learn how to switch your calculator from degree mode to radian mode. So hopefully you've got the instruction book for it still. Or you've done this before and you know how to do it. Or you'll find out how to do it. Okay? Make sure you can swap the modes. And let's go accurate to 4 decimal places. So let's go here to 4 decimal places. The sine of 48 degrees, according to my calculator, was 7431. So I should say approximately equal to, because that's rounded to 4 decimal places. So did your calculator give that? Yeah? Hope so. For this one, I got the cos of 32.5 to be 0.8434 when rounded to 4 decimal places. And for tan here, I got 0.0473 to 4 decimal places. It's interesting if you go back and have a look at this diagram here. So the people at home can't see where I'm pointing, but too bad. In our 45 degree triangle, we said that the sine of 45 degrees was 1 on root 2. Now if you work out 1 on the square root of 2 on your calculator, I think you get something like about 0.7071 or thereabouts. 0.70. So the sine of 48 degrees is about 0.74. So it's a bit bigger. So what it's saying is that as I increase this angle a little bit, the ratio of the opposite to the hypotenuse is actually getting larger. So this side is actually getting closer to the length of that side. I don't know if that's immediately obvious, but that's what it's telling us, sitting in there. We will end up with a better geometric representation of this come next week, and then you'll be able to think of all these things far more simply than just from the triangle. But for the minute, that's how we would think of it. So obviously, I would say here, the hypotenuse is the longest side of the triangle, so the ratio of the opposite to the hypotenuse has to be less than 1. This side's never going to be as long as that side. But it's saying that as the angle gets bigger and bigger, they're getting closer and closer to being the same. I think that seems reasonable. I think. Oh, and while we're at it, if I make that angle bigger and that's going up further, the ratio of the adjacent to the hypotenuse is getting longer, we're not even chasing the adjacent, so the cosine must be going down. So as we go up towards 90, the sine should be getting larger, the cosine should be getting smaller. Okay? All right. There's one more thing that we need to help us do a lot of the problems that we're going to face, and it's this here. Remember last time we talked about inverse functions, and I said to you, if you have an exponential, then the way to undo that, the opposite operation is to take the log. Likewise, if you square something, the opposite operation is to take the square root. If you add a number, the opposite operation is to subtract. So when we have a trig function, or a trig ratio here, we say that the opposite operation is going to be this thing here, sine to the minus 1. So we're going to call that inverse sine. Here, that's the inverse sine. And we've used that to the minus 1 notation again. The inverse notation that we introduced last time with inverse functions. Remember we had f to the minus 1? That meant the inverse. That's going to mean the inverse here as well. So that's not the reciprocal, it's the inverse sitting there. And so it says, if the sine of 30 degrees is 1/2, then 30 degrees is sine inverse of 1/2. So we think of this as, if I looked at that, I would say, what angle has as its sine 1/2? And the answer is 30 degrees. The sine of 30 is 1/2, so sine inverse 1/2 is 30. It's the inverse operation. Okay, so that's, for the minute, I'm just saying it's the inverse operation. Once we've introduced the trig functions, this is going to be the inverse function when we get down there. So that's our notation, our terminology. And so it says here, if I have angles between 0 and 90, i.e. I'm in my triangle, find sine inverse 1 on root 2. So what it's asking in here is what angle, and let me give it a letter, theta, Greek letter theta sitting there. What angle theta is such that sine theta is 1 on the square root of 2. That's the question that's being asked there. What angle has as its sine 1 on the square root of 2? And if I go back to my table here and have a little browse, I can see, look, here the sine of 45 degrees is 1 on root 2. So sine inverse 1 on root 2 must be 45. That's what we're trying to indicate here. So in here, I would say part A, sine inverse 1 on root 2 is equal to 45 degrees. Your calculator has on it a sine inverse button, I would imagine. Some calculators may call it a sine. and that's short for arc sine. But arc sine and sine inverse are the same thing. So have a look at your calculator, and if you put in sine inverse 0.7071 or something like that, or actually calculated one on root 2 and then went sine inverse of it, it should return, so long as it's in degrees, it should return 45 or something very close to it. So in part B, tan of theta is 3.1. I go over to my box here, have a look at the tans, and of course there's nothing there that says 3.1, so I can't do it off the box. And so in this case I actually have to use my calculator, I've got no other choice. And so this says, therefore, theta is equal to tan inverse 3.1, and I would say via the calculator, I should get something, and I'll say it's approximate. It'll be something like 72.12 degrees to 2 decimal places, which would be, if you were to convert it, something like 72 degrees, 7 minutes and 17 seconds. But that is just an approximation. So the exact answer would be tan inverse 3.1. The approximate answer would be 72.12 degrees, sitting in there. So I'll say that's exact, and this one is approximate, sitting there. Question?
So how many minutes are in a degree?
60. 60 minutes in a degree, 60 seconds in a minute. Yep. I think most of the time, I'm happy just to have decimal degrees. Okay. I imagine that your calculator also has a button on it that swaps from decimals to minutes and seconds. It should have a little apostrophe, then 2 apostrophes or something like that. Have a look on your calculator. Most calculators have a convert from decimal degrees to minutes and seconds button on it somewhere. Again, if you can't find it, come and ask me. I might be able to find it. I'm not very good with calculators. I don't use a calculator that much because I've got a computer sitting in front of me. It's easier to ask it. That's all. So that's what I've got used to doing. But I might be able to find it. Okay, and part C says cos theta is equal to 0.381. So if I want to know what theta is, that's the same as asking, well, theta must be cos inverse of 0.381. And when I did that, I got something like 67.60 degrees, which when I converted it gave me 67 degrees, 36 minutes and 16 seconds, something like that. So these are relatively easy to do, as in you just get your calculator out and press a few buttons. The important part is knowing when to do it, I guess. So let's have a look at when we might do such a thing. So as an example, it says here, what is the angle of elevation of a railway line that rises uniformly 7 metres for every 200 metres of track? So if I would draw a picture of that, it would say my railway line goes along 200 metres, and for every 200 metres it rises 7 metres. And it wants to know the angle of elevation. The angle of elevation is the angle above the horizontal. So that would be my angle of elevation in this case. Here, that's the angle above the horizontal. or from the horizontal might be another way of saying it. Now, when I have this angle here, theta, if I have a look, I know the side opposite, I know the side adjacent to it. And again, I'm going to go back to my standard page. No, perhaps I need to go back. To this page, in fact, would be better. In that it says, if I know the opposite and the adjacent, it's the tan is the ratio that I want. And so this says the tangent of theta must be the opposite over the adjacent. So that's 7 over 200. Now if the tan of theta is 7 on 200, then the angle itself must be tan inverse of 7 on 200. So I know what angle that should be. Now, clearly 7 on 200 isn't anywhere in my table of standard values. That's the one that I keep bringing up. I've only got 1 on root 3, 1 on root 3 to choose from, so it's not one of those. So I'm going to use my calculator, and when I do, I will get an approximate answer of 2. Now, I had to go a fair few degrees to get down here. So I've got a lot of decimal places sitting here. So I've gone to 2, 4, 6 decimal places there. But it's something very close to 2 degrees. And so the angle of elevation is about 2 degrees in that case. So let me just recap on a point that I think is pretty important. And I've made it before and I'll make it again. But sitting in here, if I have an angle, and I've chosen 45 just as my example, the sine of that angle is a ratio, we know that, but it's just a number. So for example, the sine of 45 degrees is the number 1 on the square root of 2. All I've done is this number and this number are written with different terminology, but they're the same number. So given that I have that the sine of theta is just a number, I can add them. I can subtract numbers, I can multiply, I can divide, and so forth. And so therefore I can do arithmetic with that number and I can do algebra with that number. So in some sense, it's really good to think of sine of theta. Okay, initially we're thinking of it, oh look, it's the ratio of the opposite to the hypotenuse, and that's important. And then after a while it's really good to think, okay, it's just a number, therefore I can do algebra with it. Right? You've got to think on 2 different levels. And that sometimes gets confusing. But so long as you can think to yourself, well, it's just a number and I can do things with it, that's good. It turns out there are some properties of trig that we're going to talk about. So I can do fancy things with this number that I can't do with other numbers. But still it is just a number. And likewise, given that I can undo taking the sine, I can solve equations that have sines and coses and tans in them. Okay? The same as last time, because I had exponential and logs, I could solve equations that had logs or exponentials in them. Same here, I can now start solving equations that have trig ratios in them. So you are thinking on 2 different levels. What is the number? And then it's just a number.